The trouble is, the weather can't make up its mind about what it is going to do until just before it does it. Our job is to find out how far ahead the weather shows its hand.
The global weather experiment will give us an extraordinary opportunity to get started on the question of why our climate behaves the way it does. Not only to help guide us in our human activities, but also to warn us in case some of those activities may possibly turn around and influence the climate itself.
The global weather experiment is the largest international scientific experiment in history. 140 nations are participating. The laboratory is the whole planet Earth. Dr. Verna Sumi, Chairman, U.S. Global Atmospheric Research Program.
For the first time ever, we'll be able to see and observe the atmosphere on all scales. The northern hemisphere, the southern hemisphere, east and west, poles and tropics.
Dr. Rex Fleming, Director and Coordinator of the U.S. effort in the global weather experiment.
Thousands of observations, computer programs, software, systems tests to check out each of the components. Ships, airplanes, buoys, satellites, all must be ready at the same time. It's just a tremendous effort. All has to go off together.
To make it all happen requires the cooperation of all nations. Chairman of the International Joint Organizing Committee, Dr. Joseph Smagorinsky.
There's been a steady improvement in the reliability of weather forecasting over the last 25 years. Much of this has come from the growing use of large computer models of the atmosphere. But it's becoming quite obvious now that any further improvements are going to require an extraordinary effort in order to increase the reliability as well as the range of weather prediction. That's what the global weather experiment is all about.
More accurate and long-range weather predictions can be of vast value to man in planning his weather-dependent activities. But we can't predict the weather with 100% accuracy at a specific time and place. Drought in this place, flood in another, the energy crunch. 4 billion people in the world, going up to 6 billion before the year 2000. Where are they going to get enough water, enough food? How much energy can we afford to get the things people need and want? Of course, most people are concerned about weather. They deal with it and talk about it all the time. To builders and engineers, it affects location of a project, startup time and pace, whether special equipment will be needed, different construction materials, when to pour concrete, how to make best use of labor. To people in transportation, it involves schedules, which route you take, maintenance, how to adapt to what can be expected from the effects of rain, heat, or cold. To the farmers, it's not only when to plant or whether a crop will succeed or fail. It's even a matter of whether fertilizer and chemicals can be spread on the surface of a field because expected rain will work it into the soil, or whether 12 tons of disking rig and tractor will have to be hauled around to incorporate those chemicals because there won't be any rain to do it well enough. To the power people, it's how much energy will be needed for darker days or longer nights, for hotter days, or cold. To all of us, it can be a matter of life and death. Every energy process we use generates heat. That's a law of physics. So with all the increased use of energy for the things we have to do, we are producing heat more than ever before. And now we have a new danger, thermal pollution. Heat held in by the blanket of our atmosphere, what some have called the greenhouse effect. How far can this go before every year we melt more and more of the polar ice cap with all the consequences that could entail for the whole planet? Or is the planet in a long-term cooling trend more significant than all the heat of civilization. These are the kinds of things we've got to learn more about. How predictable is the atmosphere? Do we know how it works? Absorbing and transmitting the tremendous radiation of the sun, held in the force of gravity, and rotating with the Earth, the atmosphere is a complex system. The lowest layer of the atmosphere, the troposphere, where most of our weather is generated, is a thin shell, like the skin on an apple. Here, water vapor rises from the surface of seas, evaporated by the sun. It is dispersed and carried along with large air masses and winds caused by differences in temperature. The spinning Earth produces large-scale, planet-wide waves which carry our good and bad weather. These waves are long-lived, and so we are optimistic about improving our forecasts. At about 35,000 feet are narrow bands of strong winds, the jet stream. These winds sometimes break down into irregular areas of very intense winds, making forecasting more difficult. Under these conditions, we sometimes have severe storms. Such irregular and turbulent motion is impossible to predict in detail, so there are limits to how good our predictions can be. Using measurements, the old way with thermometers and balloons, and the new way with satellites, we make the atmosphere visible to the computer.
Where do we get numerical forecasts? Most of these come from the National Weather Service, from observations provided by weather stations around the world. These are part of the existing World Weather Watch. The network of stations isn't too bad over the continents of the world, but it's simply not complete enough. It can't be. The reason is that the weather has global roots. We simply don't measure enough for the world's oceans and atmospheres.
What does it take? How much of the globe would we have to observe for accurate forecasts over various periods of time? For a 1 to 2 day forecast for the United States, we need information gathered from 20 degrees north of the equator to about 75 degrees north, and up to an altitude of about 10 kilometers, or about 33,000 feet. For 3 to 5 days, we need information about the surface temperature of the seas, too, and must extend our sensors still higher in the sky and south of the equator. For forecasts beyond a week, we'd have to have data from every part of the planet, from hundreds of feet beneath the sea to miles into the sky. Right now, our existing surface observation points are more or less like this. We have land stations and ships at sea. But what we really need is a full three-dimensional picture of the atmosphere. Our upper air observations, balloons, planes, and satellites, give us the profiles of temperature, pressure, humidity, but there are too few of them for long-range predictions. We get adequate weather information from only 15% of the Earth. This tells us what's happening at particular places at particular times. But weather is being generated everywhere. It's global and linked in space and time. And the gaping holes in the information grid, most of them in the southern hemisphere, are holes in our ability to forecast and in our understanding. In 1967, the long-term Global Atmospheric Research Program was begun. The experiment is part of it. All over the world, an intensive probe into atmosphere and ocean dynamics and interface is going on. For the global weather experiment, our observation points cover the globe as never before. The strategy was therefore to augment and improve the World Weather Watch and use that as the basic observation platform, to time the experiment, to make use of polar satellites and 5 new geostationary satellites that could cover most of the planet, and to coordinate agencies and scientific organizations from virtually every country on Earth. 4 polar orbiting satellites, 2 from the Soviet Union, 2 from the US, supplied temperature and humidity profiles, data on clouds, and sea surface temperatures. 5 geostationary satellites observe cloud motion and report on winds in tropical and lower latitudes. These are provided by the US, Japan, and the European Space Agency. The satellite coverage extends over a greatly expanded World Weather Watch observing system, supplemented by ship reports of surface conditions and reports from commercial aircraft. many of them equipped with automatic instrument packages rigged to their navigational systems. Still, there are gaps, mostly in the tropics and farther south. During the experiment, the area from 30 degrees north to 10 degrees north is well covered by Weather Watch land stations, ships, and aircraft. Now, from 10 degrees north to 10 south, in that important tropical band around the equator, we supplement our existing systems, especially during 2 concentrated observing periods, with tropical wind ships from more than 20 countries and specially dedicated to this project and to the oceanographic objectives of the experiment. Special U.S. aircraft releasing dropsonde instrument packages by parachute along carefully laid out tracks. And an armada of constant level balloons at high altitudes to give readings where the aircraft can't go. And in the southern latitudes, the value of the satellite systems is greatly increased by deployment of drifting buoys to measure surface temperature and pressure over vast expanses of southern oceans. These are provided by Australia, Canada, France, New Zealand, Norway, and the U.S. Assisting in the deployment of these buoys will be Argentina, Brazil, Chile, and the Soviet Union. Much of the information is radioed to satellites, stored and relayed back to Earth stations on a regular schedule. With these systems, our grid of good information should look more like this: data for a whole Earth view.
This coordinated research plan has been provided by many scientists, oceanographers, and meteorologists working with the United States Committee for the Global Atmospheric Research Program. But this is only the beginning. Research using this data will take several years and will be conducted in laboratories and universities throughout the United States and the world.
The global weather experiment should have several outcomes. First of all, we should determine what the ultimate limits of weather prediction are. We would then be in the position to say what it will take in the way of a global database and in more sophisticated computer models in order to get as close as possible to this ultimate limit.
What it means to the world is, ultimately, better control of food, water, energy. A lot of scientific work has brought us to where we are today. It will be years before all the research will be completed, but we are moving. We have shifted our point of view from here and now to what's going on in many places, and now to a whole Earth point of view, a truly international experiment.